Okay, hello everyone. Welcome to our seventh lecture in ECE 576, Information Engineering. And today we are going to move on towards another topic, uh, which is one of the components of the communication system that we've been talking about. So until now, we've developed the basic formalism with which we can measure and quantify information. But then we also have to study the different encoders that are used to perform different functions on the data before it is actually transmitted over a channel. So we've seen how the channel capacity looks like and how we can compute it if you know what the source of data is. So let's go back and look at the communication system that we've been looking at in our previous lectures. So when we have an input data, it goes through a source encoder. Right, if you remember that this is um, the message S, and then that goes to a channel encoder. And today we are going to focus on this source encoder part because we've already seen what the channel encoder looks like. And then it becomes the signal T, which is transmitted over a channel, and then where noise is added to this. And that goes on to the receiver side. So we've seen up till now that the channel encoder tries to make sure that when you transmit data, you are able to detect it correctly. So we try to, yeah, I see a question.
I have a question. I don't know if you changed anything in your system, but you're not very clean. I don't know. I cannot make up. There is times I don't know if you're far away from the speaker, but
Okay,
I can
Yeah,
hear.
I'll agree. The microphone's a little muddy today. Yeah.
Yeah.
Okay, one second. Is it good?
Oh wow. Yes, that's it.
Okay. Yeah, the wrong mic was selected. So thank you for pointing it out.
No, it's good.
Okay, so we are looking at the, we've already seen channel encoders. So what it does is it tries to make sure that whatever you send over the channel is decodable at the other end. So what you do is basically you add some redundancy that helps you correct errors in the transmission. Right, so if you remember, we added parity bits and we did all sort of Hamming codes to kind of encode the sequence into a longer sequence that helps in error correction. Right, so the purpose is we do error correcting codes here. And the purpose is really to add redundancy that helps recover from errors. Okay, so today we are going to look at the other piece of this encoding system. That's the source encoder, and the purpose of this is to make sure that your data is expressed in as few bits as possible. So basically, we want to do compression. Right, so we're looking at data compression. And the whole purpose is that we remove redundancies. To ensure that data is represented by the smallest number of bits. Okay, so you see, it's a little bit ironic because we are first trying to remove redundancy, and then we add redundancy to the input sequence. But the whole purpose is to give some structure to the input data. So first we try to make sure that your data is as compact as possible, right? So it's expressed by the least number of bits. And then the next stage is you try to add some extra bits to it that help you recover from error. Those can be in the form of parity bits or some other type of encoding scheme that's part of the channel encoder. So let's look at this data compression part. So we will consider a kind of a code that helps you compress data. So let's call that code a symbol code C, and for an ensemble X. So ensemble is really a group of bits. Okay, so for an ensemble X is actually a mapping from the possible source symbols to the code words. Okay, so this is the formal definition of the symbol code that helps you compress data. Now, let's take an example to see how symbol code looks like. So for example, a symbol code for X for the ensemble X is as follows. So if X can take the values between A, B, C, and D, these are source symbols, and their probabilities are 1/2, 1/4, 1/8, 1/8. Then the symbol code, one possible code called C0 is or maybe a possible is the following. So let's say there is the symbol X, and there is a code C of Xi. Okay, and then let's say the symbols are A, B, C, and D, and their associated code is, let's say, 1000. It's a one-hot encoding, right? If you remember, we talked about it earlier. So it's like parallel wires, and whichever one is active represents the corresponding symbol. So let's call this a one-hot encoding. Now, you can also write down the length of the code word. So here the length is called L, or let's call it Li, length of the ith code word. And it comes out to be 4 for each of them. Okay, now these symbols at the input are probabilistic. So you will get a with a probability of half, B comes with a probability of 1/4, and C 1/8, and D 1/8. So essentially, if you have a code with different lengths, then the expected length would be an average or a kind of a probabilistic average over all these lengths. So it's not always, the average length is not 4, but it depends on the probability. So you have to do an average to find out the average length of such a code. So now the question is, because we are looking at data compression, our goal is to see what is the shortest length encoding of this source X. Right, so the question that we are interested in is this the shortest length encoding for a source X? Right, so X is a random source, which is providing you with some symbols with certain probabilities. And the purpose of the encoding scheme is to figure out a code word that represents that symbol. And the length is really what matters when it comes to compression. So the question is, how do we know if this is the best possible encoding that compresses the data to the maximum limit? Okay, now let's put down a few facts before we can go into the details of codes and their properties. Obviously, there has to be some method to this, these codes and code words. We cannot just arbitrarily pick numbers to represent symbols, and we'll see what are the properties. So let's put some facts first. So in this example, the code for sending a symbol xi is represented by C of xi, right? And that's, so for example, the C of A is 1, 0, 0, 0. Okay, so this is one, let's call this notations or useful notations. Then if you concatenate a few code words, then what we can call it is something known as extended code. So extended code for the symbols xi, xj, xk is represented as by C plus, it's like C concatenated of xi, xj, xk. Okay, so for example, the code for the symbols ACD is actually C plus of ACD, and that turns out to be just concatenating the three. So A is this, C is this, and D is this, right? So we'll have, this is A, right? Then we'll have C, which is 0, 0, 1, 0. And then D is the C, and this is D. And this plus symbol here just tells you that it's an extended code, right? Extended or concatenated. Okay, now let's look at how a code should be designed, or what are the requirements of symbol code, right, when it comes to source encoders. So let's see what are some basic requirements. For a useful symbol code. So the first requirement is that a code should be uniquely decodable. So these are all technical terminologies, and we'll see how to figure out if something is uniquely decodable. Right, so intuitively it makes sense that an encoded string must have a unique decoding, so it should be a one-to-one mapping. Must have a unique so it's a little hard to check when it comes to actual implementation, because obviously when you have a table, you don't have this mapping for all the possible strings, so you don't know whether it's unique in terms of decodability or not. So the way to check is the following. So a code CFX is uniquely decodable if under the extended code C plus no two distinct strings have the same encoding. Okay, so maybe, yeah, this is the critical okay, so that means if, let's say, the string y1, y2, yk is not equals to zk, right? If two strings are not equal, then the point is that their encoding should also not be equal. Right, it's a subtle thing, but you have to pay attention to it when it comes to applying this. So that means CY2 CYK is not equals to the CZ1 CZK. Okay, so let's take an example. So let's have a code, a binary code, where you just have two code words, 1 and 01. Sorry, 101. Okay, and I mean, this corresponds to x1, this corresponds to x2. So this is uniquely decodable. Why? Because one, if you concatenate these two, that makes it 1101. That is not a code word. Okay, and so and similarly 1011 is not a code word. Okay, in other words, so the concatenations x1, x2, x1 have encodings 1101 and 1011. Okay, which are not equal. Okay, but the story doesn't end here. You have to keep looking at all the combinations. I mean, I want to emphasize that it's not straightforward to see sometimes whether something is really uniquely decodable or not, because you may not know if a certain combination turns out to have the same encodings, right? So for example, but I mean, you have to make sure that all possible concatenations are or have distinct encoding. So for example, x1, x2, x1, x2, x1, x2, and so on. Okay, in this binary case, it's simple because the moment you attach x1 and x2, it turns out to be different from x2 and x1. So it's not likely to have any concatenation that will upset this this matching, or anything that will have an overlapping encoding. But let's say you have three symbols, and one of them is 1, the other is 0, and the next one is 1, 0. Right, so obviously this is not uniquely decodable because, right, x1, x2, and x3 have the same encoding. Right, you see this? So sometimes it can be a little different. So let's say there's X3 is 101. Again, it's not uniquely decodable because you can have X1, X2, X1, and X3 have the same encoding. So similarly, you have to look at it in a, you have to see all the possibilities to come up with a conclusion. We'll see more examples later on, but for now, we're just mentioning the useful properties of a symbol code that can actually be used to do source encoding. So now the second property is it has to be easy to decode. Okay, so what does easy to decode means? Means that a symbol code is easy to decode if it is possible to identify the end of a code word as soon as it arrives. So as soon as it okay, so what that means is basically no code word is a prefix of another code word. Okay, so this is also a very important property that you have to look at. And sometimes a code which has this property is called a prefix code. Okay, so for example, for the code 1 and 101 is not easy to decode. And the reason is because 1 is a prefix of 101. So the idea behind prefix code is if you receive one bit, which is 1, you still cannot figure out whether it's the first symbol or the second symbol. You have to wait till the next bit arrives to see really whether it's the first one or the second one. So you basically cannot instantaneously say what the code or what the symbol is transmitted. So sometimes it's also called the instantaneous code or self-punctuating codes. I will write this down for everybody. So for example, if 1 is received at the decoder, it still needs to wait for the next bit to decide whether the symbol, so let's say this is A, so whether the symbol A or B has been sent. Okay, so a useful remark here that these prefix codes are also referred to as instantaneous codes, okay, or something called self-punctuating codes. Because decoding can be done without looking ahead. Looking ahead for subsequent code words. So another important remark here is that prefix codes are actually codes that can be mapped to trees. So correspond to or prefix codes correspond to trees, right? So for example, a binary tree. Now let's take an example of codes that are easy to decode or that are prefix codes. Consider a code C1 and which is a binary code and has 0, 1, or 1. And the question is this a prefix code? Okay. Now there's many ways to look at it, and I think the first one is intuitive because you can directly see if some code word is part of the other one or not, right? But sometimes it may be hard to see if there are a lot of code words. So in this case, it is really a prefix code because 0 is not a prefix, right, of 101. And similarly, 101 is not a prefix of 0. Okay, and the second way to look at it is the following, that you construct a binary tree and see whether the code words are on distinct leaves or not. So let's say this is a code C1 and it's a binary. Let's try to make a binary tree. And so the first one is 0, and then this is 1. So our first code word is 0, second is 101. So we'll have from here we will have 0 and then we'll have a 1 here. So our second code word is 101. Right, so since we are at distinct leaves, right? So it is really a prefix code. So essentially the meaning is that you cannot have two code words on the same branch of this tree. So you cannot have a code word which is here, and then you pick another one which is here, and then here. Or whatever, more than one code word or on this branch. So every branch needs to have only one code word. Obviously, you can go on to pick, in this case, you could have picked code words in this branch. That is okay, but you cannot have it on the same path. Right, so for example, 10 and 101 cannot be picked as code words if you want to make a prefix code. Okay. So for example, let's write it down. So note so C2 1 and 101 is not this is not a prefix code. So up till now we've seen first is the unique decodability, second is the prefix codes or instantaneous decodability. Now let's do a quick remark here, or maybe let's do an example first and then a remark. So example 2 here is a longer code, so consider C3, and it has 3 code words. One is 0, 10, 110, and 111. So let's try to make a tree and see whether it is a prefix code or not. So the tree will look like the following. So C3, we have 2 branches. One is 0, the other is 1. And then next time we have another 2 branches. And then again 2 branches. Okay, and yeah, that's it. So let's mark our code words. So first one is 0, the other one is 10, and then 110. Okay, so in this case, our code words are on different branches of the tree. So this code is really a prefix code. Well, since the code words are on different leaves, so C3 is a prefix code. Now, a small comment on the relationship between prefix codes and uniquely decodable codes. So if you have a prefix code, it is always uniquely decodable. Okay, so if you have a uniquely decodable code, it may not be a prefix code. Okay, so for example, C2, right? So it's our code C2, which is 101. It is not prefix code, right? But it is uniquely decodable. So for example, C2 1101 is uniquely decodable. So essentially, prefix codes are a very small piece of the entire code space of codes, right? Because they're special ones since they lie on the branches of the tree. You can have more codes, but obviously they will not have this instantaneous decodability property. It's nice to have it, but it is still okay if you don't. So the next property or the next kind of requirement for useful symbol codes is to have maximum compression. So the third requirement is that that code achieves maximum compression. Okay, so this basically means that the code has a minimum or minimum average length. Length L, C of n x. Okay, so let's see what this average length of the code is. We've already seen code with code words and their lengths, but we didn't look at the average length of the code. So important fact here, the average length of the code C with ensemble X is defined as LCX is the average. So because it's a random variable, so you have to take the expected value. So what you have is the probability x equals to x times the L of x, right? And where this piece here is the length of code word x. Okay, so you take the average over all the possible x, then you get the the average length of the code word, which is capital L. Sometimes we can also write it as PI-LI, right, where LI is the length of the ith code word and PI is the probability. You just try to multiply them and add them all together over all I. Now let's take an example. Maybe I'll just highlight this part. So consider a code. So consider ensemble X is composed of 4 different symbols with probabilities. P of X is 1/2, 1/4, 1/8, 1/8, right? The same old example. The code so let's say the code C3 is as follows. So you have XI, which are your symbols, then you have the code of code word that represents that symbol. You have probabilities. Okay, so you have code word A, B, C, D. The code word is 0, 1, 0, 1, 1, 0, and 1, 1, 1. The probabilities are 1/2, 1/4, 1/8, 1/8, and we'll also represent here how much is the Shannon information content of that symbol. Okay, so or let's first write down what the length is. So Li is 1 here, Li is 2 here, 3 here, and 3. And let's also write down what is log 2 of 1 over pi. Let's remember, if you from previous lectures, this is the Shannon information content of the symbol. So if you take the pi, take the inverse and then use the log 2, you will get this quantity here. And if you do it, you will see that you get the same as the lengths. So you'll get 1 here, which is log 2 of 2. And then you will get 2 here, 3 here, and 3 here. So interestingly, this is a code where each symbol is represented with a length that is equals to the Shannon information content of the of that symbol. So I mean, we have picked a code that actually is the best in terms of the length to represent this code. We will see that later. Now, first thing I want to mention here that the code C3 is a prefix code. Okay, so prefix codes are always the best because they are uniquely decodable automatically, right? And hence, yeah, this property is coming from the remark here. Where did I go? Yeah, from this piece. You guys should also circle this. which essentially means that if you have a prefix code, it's always uniquely decoded automatically, but not the other way around. Okay, so you just have to be careful when using this argument. Now, if you look at this code, the average, right? So L, maybe just say average length L, C3, and X is actually the summation Pi Li, and that turns out to be half times 1 plus 1/4 times 2 plus 1/8 times 3 plus 1/8 times 3. Okay, so that turns out to be 1.75. Okay, and obviously in this case, because the length is equal to the log 2 1 over pi, that is the information content. So if you average the information content, obviously you get the same result. So in this case, it turns out that that average information content is also the same. So if you recall, the average information content was referred to as the entropy of the source. So this average information content is actually equals to the average length of the code in this case. And we will see that this is really the best we can do when it comes to coding and to a source code that we want to compress. So this is the best compression we can achieve. We will see this with more examples in the coming parts of the lecture. Now let's take another example. With another code. So consider C4 as follows. So again, you have those A, B, C, D. Oops. Okay, so we have A, B, C, and D. And let's say the code words are the following: 0, 0, 0, 1, 1, 0, and 1, 1. So this is the binary encoding standard. So using the same probabilities, 1/2, 1/4, 1/8, 1/8. So now if you look at the lengths, we just have length of 2 bits for all these symbols. And if you look at the entropies this time, entropy or not entropy, but the information content, that turns out to be 1, 2, 3, and 3, because that's the same since it depends on the probabilities only. Now, notice that C4 is a prefix code. Right? And the reason why it's prefix is because, again, you can check out the tree. Remember, we have 0, 1, 0, 1. So our codes are what 0, 0, 0, 1, 1, 0, 1, 1. So it's a prefix code. Now this average length for this code is clearly 2. So let's write it down. LC4X.
How can you tell if it's a prefix and if it's not? That what you said.
Yeah, prefix code is easy to figure out because if your code words are on distinct leaves of the binary tree, then it's a prefix code. So in this case, I showed you that we are not picking 2 code words on the same branch. Everything is on a different leaf. So remember, if you pick 0, which is here, and you pick 0, 0 as 2 code words, then that code is not a prefix code.
Yeah.
But if you pick code words on different branches, then that's okay. That's a prefix code. Okay, so if you take a look at the length, in this case, it's PI, LI, but you see all the LIs are the same. So essentially you will get what, 2 times, or let's say half times 2 plus 1/4 times 2 plus 1/8 times 2 plus 1/8 times 2. So it turns out to be 2 bits, right? Which is actually greater than the entropy. Okay. Now, let's take another example to see if something less than the entropy can be achieved. So consider C5, another chord. So you have xi, c of xi, ei, li, log 2 1/pi. Okay, so we have A, B, C, and D. And your code is 0, 1, 0, 0, 1, 1. Okay, probabilities are again from the previous example. Now the lengths here are 1, 1, 2, and 2. And the information content is 1, 2, 3, and 3. We'll just move these down. Okay, so if you take a look at this example, what you will notice is, first thing is it's not uniquely decodable. So code C5 is not uniquely decodable. And reason, again, you can construct the tree. Right, so you have 0, you have 1. Right, so your first code word is 0. Your second code word is 1. And the next code word is actually 0, 0. So your next code word is 0, 0, and then you have 1, 1. Right, so since the code words are on the same branch, of the tree, C5 is not uniquely decodable. Okay, now the second thing is about the length. So let's look at the average length of C5, which is L C5 of X, and again it's for all I you do PI LI, and in this case the lengths are 1, 1 and 2, 2. So you will have half times 1 plus 1/4 times 1 plus 1/8 times 2, 1/8 times 2, and what you will get is about 1.25 bits. Okay, so notice this is actually smaller than the entropy of X. Right, do you see this? Entropy of X was 1.75 that we had in the previous example. And now we actually achieve a code length or average length of the code, which is less than the entropy. Now, important thing to note is that we lost something in this process. We lost unique decodability. Now, what this means is we can achieve an average code length less than the entropy of X, but we lose on unique decodability of the code. Okay, so what we'll see in the subsequent sections of this lecture is that how do we find, I'm sorry. Just give me a minute. Yeah, so we'll see what are the best lengths of the code and whether that's the optimal or not. And that's the starting point of the idea of compression, because we want to have minimum lengths of codes to represent our source data. So let's take a motivating example on data compression.
Can you go back to the entropy, Professor?
Okay, one second. Which part?
Where you say 175 is equal to the entropy of the.
Yeah. I mean,
So we're using the same formula. Why is this the entropy and the others?
so entropy actually just depends on the probabilities, right? So this will give you this.
Okay.
You see this? So this is not going to change. Now the entropy is just the average of this. Maybe I should write this down. So what is h of x, right? Is actually summation pi log 2 1 over pi, right?
Yes.
So that's going to be half times 1 plus 1/4 times 2 plus 1/8 times 3. So this is 1.75.
Okay, now I get it. It was like, how can the same formula give us this? Okay.
Yeah. So I mean, that's the average information content. It's 1.75, but that's exactly equals to the average length, because here the lengths are the same as the information content.
Understood.
Yeah. In other cases, you see lengths are larger than here. Lengths are smaller than the.
Got it. Then.
Yeah. Now, well, let's take another example of the of a code. So let's consider a code C6 as follows. So we have xi, again pi, li log 2 1 over pi. Okay, again A, B, C, D. Now this time the code is 0, 0, 1, 0, 1, 1, 1, 1, 1. So PIs are half, 1/4, 1/8, 1/8. And length this time is 1, 2, 3, and 3. 1, 2, 3, and 3. So obviously this is it's slightly different, right? So remember, now we have the same length as the information content, but the code is not the same. It's a different code. Now, question is it a prefix code? Let's see. Let me just move these. So the first thing is it a prefix code? I want all of you to look at whether it is or whether not.
No, it doesn't look like a prefix code.
Okay. Yeah, so no, the reason again, we can make a tree. You don't have to do any guessing here. This is 0, 1. Right, so your first code word is here. Okay. And then the next one is 0, 1. Okay, so obviously directly we can conclude here that it's not prefix because we have already had two code words on the same branch. So 0, 1, and 1. So no, because more than one code word. On the same branch. Okay, now next question is it uniquely decodable? Let's look at it again. So unique decodability means that no possible concatenation of code words end up in the same encoding. Right, so if you combine A and B, it's 0, 0, 1. That's not a code word. So I don't see, at least from a observation point of view, whether this can easily be confused. Right, 1, 1, 1 cannot be confused with any other, no matter how you concatenate it. So yes, it's uniquely decodable. There's no standard process, but you have to look at all the possible combinations. And from observation, it seems like there is no possible. Yes, because it is not possible to find two sequences that end up with the same encoding. Now, so the next one is it easy to decode? So it's not. And let me tell you the reason why. Because if 0, 0 is received, we may interpret as AA or AB or AC. You see? So AA will be 0, 0, right? AB will be 0, 0, 1. AC will be 0, 0, 1, 1, right? So it's not really So from 1 bit, you cannot figure out whether, even from 2 bits, you cannot. So you have to look at the third one to figure out what really is that symbol. And even though you have 0, 0, 1, you don't know whether this 1 is part of the symbol D or not. So this code is not easy to decode. But interestingly, it still has a nice structure of lengths that's actually equal to the entropy of that source. Now, question is, what is the limit imposed by unique decodability?
You go to that tree for a second.
This tree?
Yeah. Is 0, 1, it's supposed to be on the other leaf or?
Yeah, I'm sorry. You're right. Yeah, this is 0, 1. And then 0, 1, 1. Yeah, that's right. So what you see, we have 3 of them on the same branch. Okay, so I'm going to give you a result here. We're not going to prove it, but you can find the proof if you're interested. So that's actually a limit imposed on uniquely decodable codes, and that's called the Croft inequality. So what Croft inequality says is that for any uniquely decodable code C of X over the binary alphabet alphabets 0 and 1, the code word length must satisfy the following inequality. Right, so that's summation over all I 2 to the power minus Li should be less than equals to 1. Okay, so that's a very important result that you can use to see whether code length can actually form a uniquely decodable sequence or not, or uniquely decodable code. Now this, so this 2 here basically is because of the binary alphabets. Okay, so you can actually generalize it to any base. So this 2 is used for binary alphabets. So in general, it is d to the power minus Li in general for base d. Okay, so now a quick remark is that Croft inequality is actually a necessary condition. Condition for unique decodability. Okay, but you have to make sure that you know that this is not sufficient. So in other words, if if a code word or if a code does not satisfy this inequality, then it cannot be. So it is certainly not uniquely decodable. Okay, but if it satisfies, then it may still not be right. So if the code satisfies, it may still not be uniquely decodable. So, I mean, this inequality can help you clean up your or try to eliminate codes that are not uniquely decodable. So if a code word or code word length does not satisfy Croft inequality, then you can safely assume that it can never be uniquely decodable. But obviously, I mean, the space is larger. So, I mean, these are uniquely decodable codes, and a small piece of them actually satisfy a Craft inequality. Right, so let's say this is it's the other way around. So it's okay, and then you have a small piece here which is uniquely decodable. Right, so there's space for codes for which Craft inequality is satisfied, but not uniquely decodable. But obviously anything outside can never be uniquely decodable, right? So if anything is here, it can never be a uniquely decodable code. So that's an important property to know here. And let's take a quick example to see how we can make use of these. And then these figures actually help you see how Craft inequality can be looked at from an illustrative point of view. Okay, so let's see an example here. So the code C5 that we saw earlier has lengths 1, 1, 2, and 2. Okay, so the sum of I 2 to the negative li is actually 2 to the power minus 1 plus 2 to the power minus 1 plus 2 to the power minus 2 plus 2 to the minus 2, and it's actually 1.5. Right, so it's actually larger than 1. So Kraft inequality is not satisfied. So C5 cannot be uniquely decodable. Okay, now another remark here which says, so if a uniquely decodable code actually satisfies the Kraft inequality exactly, satisfies exactly, so that means the sum of 2 to the power minus Li over all I is exactly equals to 1, then that code is called a complete code. A complete code, and an example would be the C3 that we saw has actually the exact lengths that lead to a Kraft inequality of 1. Yeah, this code. So 1, 2, 3, and 3. Now, another fact here is that complete codes and the reason it's called complete is because you actually fill up the whole tree. So corresponds, so complete code corresponds to a complete tree having no unused branches. So if you look at the C3, this one, so that's a code which we don't have any unused branches. So if I draw it for you, you see there's one code word here, and then we have 1, 0, okay, and then 1, 1, 0, and then 1, 1, 1. So all the branches have been used. You don't have any left, right? So that's the idea of a complete code. Now let's look at the illustrative examples on Kraft inequality. to see why it makes sense. Obviously, I'm not trying to prove it here mathematically, but I can show you with a diagram why this is true. So why codes that are uniquely decodable have to sum up to something that is less than 1. So so let's see. Let's take an example here. So let's take a look at this image. Yeah, let's pull them, all of them, downward. So essentially, this diagram is a tree. It's drawn in the form of a table. What you can see is it's like a tree. So the first half is 0, and then there is 1, and then out of this you get 0, 0, and 0, 1, right? And so on. So it's like a tree drawn. Now and so on. So, but we're not going to look at the tree here. Imagine that, you know, this is like the size of this block is 1. Right, so imagine the total size of the block is 1. Okay, now so the first block here, which is this, is, for example, here, right?
Is there a unit? Is there 1 bit or?
Yeah, it's a code word. So if you have a code word 0, that's going to occupy this much space. So each code word occupies a size of 2 to the power minus Li, where Li is the length of the code word.
So when you say size, you're referring purely to the vertical aspect of this graph, right?
Yeah, vertical
Okay.
of this box here.
Okay.
So we can only have like code words that can add up to 1. So what we said is the summation 2 to the power minus Li is less than 1 if things are uniquely decodable. And for unique decodability, we said you cannot have codes that are on the same branch. So what that means is if you picked this block here, you cannot pick this one. Obviously, you have to, if you want to pick something, you can pick this as a code word. Otherwise, it's not going to be uniquely decodable. So what Craft inequality says is that the size that you occupy is going to be 2 to the power minus Li. So if you pick the 0 as a code word, it occupies size 2 to the power minus 1. Right, because it's length 1. So it already occupies half your budget or total block. Now, let's look at a code C0. So that's our first example here, where the shaded ones are actually the code words that we pick. So let's call this our example 1. So these are the code words that you've picked. So this is one, this is second, this is third, this is fourth. Okay, so the question is, does this satisfy craft inequality? So remember this, the block is actually representing the size that it occupies. It's actually 2 to the power minus 4, which is 1 over 16. Right, so if you only have these 4 code words, then obviously you add their sizes, you're going to be less than the total block size. So it's clear that if you just have these code words, then yes, you satisfy the craft inequality. Okay, and the reason is because the sum of 2 to the power minus li is less than 1. Obviously, you can go and start checking by implementing this formula. You have 2 to the power minus 4 plus 2 to the power minus 4 plus 2 to the power minus 4 plus 2 to the power minus 4 will come up to be something which is, I think, 1 over 4. So it's less than 1. But obviously, you can use this chart to see whether all of these add up to the block vertical block length or not. Okay, so if I ask you if this is uniquely decodable or not, well, this is, because obviously there's no overlap in the horizontal direction. Right, so this is one. Let me just write it down. Is this a prefix code? And the answer is yes, because no horizontal conflict in the chart. Okay, so I mean, this is one basic example, but let's look at other examples. Let's take the example of this code C3. Okay, now this code, obviously you see that you picked 0, 1, 0, 1, 1, 0, and 1, 1, 1. So from just by looking at it, I can see that this is a complete code, right? Because all the branches of the tree have been used and just adds up to exactly 1 if you do the craft inequality. Right, so I will just put some comments here. So this is a complete code. So you see, the thing is, we have multiple options to when it comes to coding. So from this chart, you can pick any code words. You don't have to add up to exactly 1. So for example, the first code word, this one does not add up to 1. It's much less than 1, but still it can be uniquely decodable. It can represent 4 symbols, but you can also pick a code that is complete, which means that fully utilizes the margin offered by the craft inequality. So that is the sum of 2 to the power minus Li is equals to 1. Okay, and the code is a prefix code. Because node to adjacent, node to horizontally horizontal boxes are filled. Right? So in other words, if I pick this as a code word 2, then obviously it is not a prefix code, because we have picked 2 of them on the same branch of the tree. Okay, now let's look at other examples. Let's see what C4 looks like. So this is example 3. Now this code, first of all, satisfies craft inequality exactly, right? Because you can see you have filled up the whole space. Okay, so satisfies exactly, and is also a prefix code, since no 2 boxes are filled horizontally, right? So therefore, this code is uniquely decodable. So you see, the whole point is we have many options to pick from when it comes to codes, and they have different properties like unique decodability. They have properties like being prefix code, right? And also easy to decode or instantaneous decodability. So this chart helps us to see whether you satisfy the craft inequality or not, which is a necessary condition to be uniquely decodable. And hopefully, if you satisfy it, you may still not be uniquely decodable, but at least what you can see is if the code is prefix, then automatically from our remark, from the remark here, so hopefully if you can establish prefix properties, then you can immediately say it is uniquely decodable. Right, so you have to make use of 2 of these. One is to see whether the selected codes are within this box, right? And hopefully they satisfy the craft inequality. Then if you can see that they are also prefix, then amazing, you are in the uniquely decodable regime. Let's look at the other example that kind of is different from the other ones that we saw. So here it's an interesting example. So what we have here is, again, 4 code words. So you picked 0, and then you picked 0, 1, and 0, 1, 1. So first thing is obvious because we have boxes shaded laterally or horizontally. So does it satisfy craft inequality? Now we have to look at it, right? So it's not very obvious because So so this box is actually this box, right? And this box can be transferred here. So of course this adds up to 1, right? So that's good. But you see that this Kraft inequality, you've seen a counterexample here. So even though, so this code satisfies Kraft inequality exactly, that is summation 2 to the minus li equals 1, but this is not a prefix code. So it's not useful to just have Kraft inequality being satisfied. It's great to have it because it can help you at least eliminate those that are clearly not uniquely decodable.
Is it still by definition a complete code because it's equal to 1, the size?
No, it's yeah.
Okay.
Because we have to complete the tree.
Oh, okay. I see.
So this is not a prefix code since boxes or of course boxes are filled horizontally, right? So we have conflicts here.
When you say the box 0, 1 can be mapped into 1, 0,
What? What are you saying?
when you said earlier box 0, 0, 1, the second one can be mapped into 1, 0.
Mm-hmm.
What do you mean by that?
Yeah, actually, I was trying to figure out what is the sum of 2 to the power minus li. So I know that the size of the box represents the size it occupies in this in this term. So to see if they add up to 1 or not, I can just move this here, right? And then I can move this one here. So I see that I have filled this length, I filled this length, and I filled this length. So that all of them add up to 1. It's just a quick way of seeing it visibly. I mean, you don't have to do 2 to the power minus li and add up. Right? If I do this, then I have to compute 2 to the power minus 1 plus 2 to the power minus 2 plus 2 to the power minus 3 plus 2 to the power minus 3. So I have to do some math to figure out this is actually 1. But I can do it just by looking at this this chart. Do you see this?
Yeah.
Okay, so what I said is this is not a prefix code because obviously 0 is a prefix of 0, 1, and then it's also a prefix of 0, 1, 1. And again, 0, 1 is a prefix of this one. So clearly it's not a prefix code. So what it means is, so therefore C6 cannot be uniquely decodable. Despite the fact that it satisfies the Kraft inequality exactly. Okay, so I think that was the main topic of discussion for today, to see how we can do source coding, and we've started it. So the first thing is to see what are the properties of codes. We haven't seen any code yet, but at least if you're given a code, you can see whether it satisfies certain properties or not, and why they are desirable. So let me write down a quick summary here before we kind of end the lecture. And next lecture, we're going to look at an optimal code that can be used for compression. It's called the Huffman code. It's uniquely decodable, and it's also an instantaneous code. So that's one example of a code that can achieve compression, and it's also used in practice. But we will also see other type of codes like the Lempel zip coding, which is popularly used in your zip compression and RAR compression. So these are practical techniques that are actually used on computers to compress files and data. And we will also see some arithmetic coding schemes to do compression. So that's going to be part of our next lecture in this course. And hopefully then we are going to move on to topics in inference. We've already seen the information theory part of the course, and the next lecture or so is kind of geared towards the coding theory. Again, these are big topics on their own, and you can go deeper into any one of them if you're interested. But this course really wants to give you a familiarity with all these topics so that you have an understanding of how the information that we deal with today is processed, is transmitted, and stored. So it's going to be an interesting few lectures coming up. Now, the summary points from what we learned today is the following. So one is the start off with the end. So we saw this graph inequality, which says that if a code is uniquely decodable, its length must satisfy less than 1. So for any length satisfying craft inequality, there exists a prefix code with those lengths. Okay, so I mean, it's actually intuitive because we've seen this big chart here, and hopefully if the size of these boxes that we have to pick are smaller than 1, which means it satisfies Craft inequality, then obviously there is a provision, or there's a possibility that you can put them in places that make them prefix codes, right? So in other words, if you so there exists, meaning, you know, you can always place them in places where you don't have any contiguous selection laterally. In the diagram of Croft inequality. Okay, now the other summary point that you should take away, or the key insight that we have from today's lecture, is that the most compression that we can hope for a uniquely decodable code is, and remember this is the critical thing here. So the most compression that you can achieve for a uniquely decodable code is actually an average length of Cx, which is bigger than the entropy of the source X. And remember, this is equality if Croft inequality is satisfied exactly. Okay, and also note that LCX less than h of x is possible, but we have to compromise on unique decodability, right? Which is no good, because obviously we want to have a code that's uniquely decodable. Otherwise, what is the point of having the code? Because you may not be able to infer what was transmitted when you look at a sequence. So last thing I would say is actually is a sequel of what we already saw. So oops. So the third main thing is the source coding theorem, which we haven't seen explicitly, but it's a straightforward idea, and I'm going to put it here, which says theorem for symbol codes. So it says that for an ensemble X, there exists a prefix code C with expected length satisfying LCX bigger than h of x and less than h of x plus 1. Okay, we're not going to do a proof here, but its result is intuitive because you see that the entropy, we've already seen this part here. And what we have to show is the average length is actually always less than the entropy plus one bit. And again, that's intuitive because I mean, by averaging over all the symbols, you are not going to exceed 1 bit more than the what the entropy tells you. So if you have 2 bits, if you have 4 code words, then obviously 2 bits are enough, right? So depending on the entropy was 1.75, but obviously you wouldn't be able to exceed 2.75 in all cases, right? Hopefully, if that code is prefix code. So it has to do with the tree. You can just you can construct a tree of prefix codes, right? So that means you have to pick these codes. So whatever the probability distribution is, your average code length is always going to be less than h of x plus 1. That's an upper bound. Again, there has to be proof for that, but we are just providing the result here and not going into the details. Okay, so I guess that's it for today, and I'm open for questions if people have concerns.
Professor, I had sent you an email yesterday. When you get a chance, please look at it and give me a reply.
Oh, and did I miss the email?
Yes. It was yesterday, I think yesterday morning.
Oh, okay. I have got your email. Okay, so that's about the quiz question.
Yes.
Okay, I can get back to you. It's a little bit detailed, so let me get back to you after the lecture.
Okay, thank you.
Any other concerns? Okay, so we are going to have our homework number 3 this week, and I've already given feedbacks on project abstracts, so please take a look at those. Homework grading has been initiated, so I think along the way you will also keep getting grades for previous homeworks. Will be next Monday project feedback. Has been and I think yeah, I think we are good. So next lecture, I think we will see source coding schemes Hoffman, which is the one of the most famous and optimal coding scheme. Okay, that's it for today. So let me know if you have concerns, and feel free to send me an email later on as well.
Okay, thank you.
All right, thank you then. Bye-bye.
Yeah, bye.